Hello and welcome to the Space Above Us, episode 157, Space Shuttle Flight 79, STS-79. Blaha to go. Last time, we talked about the material and life science-focused flight of Columbia on STS-78. While we spent some time learning about how rocket engines mix their propellant and why they do it the way they do, the main focus of the mission was inside the Space Lab module residing in Columbia's payload bay. There, we studied metals, crystals, and fluids to get a better sense of how materials behave in space, while also poking and prodding our valiant crew to better understand how humans behave in space. One experiment sounded particularly unpleasant, using electrically charged needles to force extreme and painful contractions in the crew's muscles. Yikes. Thankfully, on this flight, the only uncomfortable contraction will be Shannon Lucid's spine as she returns to life in 1G. That's because STS-79 is the fifth shuttle mission to the Russian space station Mir, where we'll be docking for the fourth time, delivering our third long-term NASA astronaut to where two countries will be working together on one space station. Today we've got a full crew of spaceflight veterans, so it's all familiar faces and no learning about where people went to school. Commanding the flight is Bill Reedy, who's moving over to the left seat. With this flight, Reedy wraps up a sort of interesting spaceflight achievement. He flew as a mission specialist on STS-42, where he helped to do science in Space Lab, a pilot on STS-51, where he helped to deploy ACTS on TOS, and now as commander, he's flying to Mir. 3 different roles on 3 different missions. Reedy was actually working in Star City in Russia as the operations director for NASA when he picked up the day's faxes from a pile on the floor and discovered that he would be commanding this flight. This is his third and final mission. Joining Reedy up front is today's pilot, Terry Wilcutt. When we last saw Wilcutt, he was the pilot on STS-68, the Space Radar Laboratory 2 mission. This marks his second of 4 flights. Moving back on the flight deck, we meet Mission Specialist 1, Jay Apt. When we last saw Apt, he was helping out on STS-59, the Space Radar Laboratory 1 mission. This marks Apt's fourth and final flight, with his first being STS-37, which deployed the Compton Gamma Ray Observatory. Right in the middle of the flight deck, we find Mission Specialist 2, Tom Akers. When we last saw Akers, he was tooling around outside on some relaxed, low-stakes mission that didn't have anything at all to do but, rescue the Hubble Space Telescope. Today, he won't be heading outside, but by visiting both Hubble and now Mir, he will have flown to 2 different orbital destinations, perhaps making the crews of free-flying shuttle missions jealous. This is his fourth and final flight, with his first being STS-41, which deployed the Ulysses Solar Probe. Moving downstairs, we run into Mission Specialist 3, Karl Waltz. When we last saw Waltz, he was flying on STS-65, toiling away in Space Lab on IML-2, presumably dodging his flying and cape-wearing commander, IML Man. This is his third of 4 missions. And last but certainly not least, Mission Specialist 4, the Space Above Us favorite, the one, the only, the John Blaha. We first saw Blaha way back on STS-29, which deployed TDRS-D. His next flight, on STS-33, came only 8 months later as he hopped right back into the pilot's seat to substitute for David Griggs, who had been killed in a vintage World War II airplane crash. He returned to space as a commander on STS-43, deploying TDRS-E, and STS-58, a successful life sciences mission that helped push the upper boundaries of the orbiter's mission duration. Today, as he puts it, he'll be flying as a piece of luggage, since his role on STS-79 is to just enjoy the ride to Mir. Once there, he'll swap with his STS-58 crew member, Shannon Lucid, and become the next American to live and work on Mir. This is his 5th and final flight. Once we actually get to the countdown, it's gonna go smoothly, but STS-79 had a few delays before it could get to that point. The first delay came in the form of Hurricane Bertha, which required Atlantis to be rolled back to the safety of the vehicle assembly building. While there, the decision was made to restack the vehicle with a new set of solid rocket boosters, after the alarming discovery of signs of blow-by in all 6 field joints on the SRBs used on STS-78. The cause of this blow-by was determined to be a new type of adhesive that was being used for the first time. The reason for the switch was that the chemicals used in the old adhesive weren't all that friendly to the ozone layer, so it was being phased out across the entire country. Now, before you shake your head at the idea of replacing a perfectly functional adhesive with a new and untested one, it was tested. Thiokol, who had split up from Morton Thiokol back in 1989, did a full-scale test with the new adhesive and everything worked great. But, and this is where you can shake your head, the test was in Utah, and apparently nobody accounted for the fact that the humidity is a little bit lower in Utah than on the coast of Florida. The investigation determined that if this new adhesive was exposed to humidity for a long time and experienced larger but within spec deflections of the SRB joints, it lost significantly more strength than the original adhesive, leading to the observed blow-by. Thankfully, this didn't actually turn out to be a flight safety issue, thanks to the joints being redesigned after the Challenger accident. So STS-78 completed its mission safe and sound. But just to err on the side of caution, Atlantis was destacked and fitted with a new set of SRBs that used the old adhesive. Oh, and just as a side note, remember that blow-by I mentioned back on STS-70 and STS-71? Thiokol quickly developed a new process related to the thermal barriers around the problematic joint and completely solved the problem for the remainder of the program. So that's a nice resolution. Back on STS-79, Atlantis rolled back to Launch Pad 39A with a new set of SRBs, only to be turned around again by Hurricane Fran. Florida. But after more than a month of delays, it was finally time to actually attempt a launch. That launch attempt was smooth as silk, with no unexpected holds. And on September 16, 1996, Atlantis lit up the early morning sky, taking off at 4:54 and 49 seconds a.m. Eastern Daylight Time. After the other alarming discovery of STS-78, with the main engines nearly running out of fuel, today's main engine mixture ratio was set to a more conservative 6.02, so no fuel worries there. And since I've mentioned the SRBs and the shuttle main engines, I don't want the third pillar of the main propulsion system to feel left out. So I'll mention that on this flight, the range safety system for the external tank was removed. It was deemed to be no longer necessary, especially since the shuttle was so far from populated areas by the time the SRBs separated. So the complexity, risk, and mass of the range safety system could be removed from the ET. But actually, we're still not quite done with the SRBs. While Atlantis would soar through a seemingly uneventful ascent, the big white boosters once again had a nasty surprise in store for the engineers inspecting it after recovery. First, up in the forward skirt near the top of the booster, a 7/16" Armstrong combination wrench was discovered. A wrench. Someone apparently just left it behind. In response, more stringent tool tracking was implemented, so no more wayward tools would inadvertently be sent to the edge of space, potentially damaging the systems they were hitching a ride in. But even more concerning was the state of the nozzle down at the bottom of the SRB. The protective lining of the nozzle had been worn away so badly that it used the entire safety margin and even ate in a bit past that, leading to negative margin. It was the worst erosion seen in the entire history of the program. I dug around pretty hard to learn what the resolution to this nozzle erosion issue was, but just wasn't able to find anything in the time available. If anyone has a clue, please shoot me an email. In any case, clearly the folks at Thiokol still had some work to do. But all of that is a problem for the future. For now, the crew has just arrived on orbit and has their own problems to work through. Thankfully, they're a little more manageable. First, Auxiliary Power Unit 2 shut down on its own shortly after main engine cutoff. This isn't great, since APUs are critical for a successful landing. Without them, the pilot crew can't move the control surfaces, which is generally not great for control. Thankfully, after some quick analysis on the ground, it was determined that this wasn't a major cause for concern, and the full duration mission could proceed as planned. The crew also had to do some tests on the onboard water supply after some alarms were sent from one of the fuel cells. The fuel cell briefly reported a high pH level, but engineers suspected that this was a false positive commonly seen on new and newly refurbished fuel cells. To make sure, the crew did an actual litmus test on the water, which Sort of made me laugh because I kind of forgot that a litmus test is an actual physical thing and not just a figure of speech. This was important both for the health of the crew, but also because a lot of water would be transferred to Mir, so it had to be within specs. By Flight Day 3, the distant point of light that was the Russian space station Mir was growing brighter and brighter. Docking day had arrived. When the orbiter was trailing Mir by only around 15 kilometers, the pilot crew fired the terminal phase initiation burn, causing Atlantis to drop down and scoot underneath the station. Once arriving at the R-bar, the imaginary line connecting Mir to the center of the Earth, Commander Reedy took over manual control and began the final approach. As you can imagine, docking a massive vehicle like the Space Shuttle Orbiter to another massive vehicle like Mir is not a trivial thing to do. But it's not simply a matter of just needing to be an excellent pilot. The challenge comes from multiple competing constraints. First, there are the conditions under which Atlantis must arrive at Mir. It must be aligned side to side to within 2.5 centimeters, and rotated to within 1 degree of the correct angle. Considering that the orbiter is over 3,700 centimeters long, 2.5 centimeters is not much margin. But the orbiter must also arrive within specific velocity tolerances. The orbiter docking system must come in contact with Mir's docking module at no more than 3 centimeters per second. That's about 0.07 miles per hour. But on top of all that, the docking must take place over Russian ground stations. The Russian equivalent to TDRS was run by the military, and it was expensive for the space program to use it, so they avoided it whenever possible. So the commander must take all these other constraints into consideration, while also ensuring that the docking takes place within a time window only a few minutes long. This difficulty explains why the entire thing is really a team effort. At the end of the day, it's Commander Bill Reedy who's responsible for making it happen. He was stationed at the back of the flight deck, looking up through the overhead windows, while operating the rotational hand controller with his right hand and the translational hand controller with his left. Up front in the commander's seat was pilot Terry Wilcutt, who was punching commands into the computer to queue up the upcoming burns and ensuring that the computer was in the proper state. Mission specialist Karl Waltz kept the various cameras in focus and kept an eye on the docking adapter. Mission specialist Tom Akers, as the flight engineer, kept an eye on all of the shuttle systems. Mission specialist Jay Apt kept their place on the master checklist and ensured that all the steps were being accomplished. And luggage specialist John Blaha enjoyed the sight of a well-oiled team doing their job. Without the usual variety of anomalies and complications thrown at the team during training, the real thing was smooth and uneventful. The two vehicles made contact, the structural hooks latched into place, the automatic dampers kicked in, and once again Atlantis and Mir were hard-docked. In an oral history, Commander Reedy talked about how after docking and in the minutes leading up to the hatch opening, it's actually possible to hear the people on the other side and carry on a conversation. Something about the idea of hearing people talking on the other side of the hatch really struck me as a cool moment. 2 days, 20 hours, and 46 minutes after lifting off from the Kennedy Space Center, the hatches were opened and the two crews celebrated. Exhibiting the mentality typical of all shuttle crews, the members of STS-79 attempted to dive straight into the work at hand. Mir Commander Valery Korzun was having none of that, though. These 9 friends had been reunited, and it was time to relax and catch up. Korzun ushered the shuttle crew into Mir, where they gathered around the dinner table in the base block and enjoyed a traditional meal of bread and salt. Once the crews had enjoyed their meal and each other's company, now they could get to work. As the crew got to work, the difference between the short-term shuttle crew and the long-term Mir crew became apparent. Pilot Terry Wilcutt recalled in an oral history, quote, "When you get in space, adjusting to zero gravity takes a while. Usually by flight day 3, you're adapted to where you're not bumping into everything. You think that you're pretty good up there by the middle of the flight. You move around easily, you're not hitting anything, your feet aren't getting in anybody's face. Then you see someone that's been up there a long time like Shannon. She was just like a cat. She would just zip in and stop and just hold her position. Her gracefulness and zero gravity was so different than ours." One unplanned task was to repair the cross-shaped indicator on the docking module used by incoming shuttle commanders to ensure proper alignment. In the harsh conditions of space, some of the black paint was starting to peel off. Since it was desirable to maintain the high contrast of the black paint against the white background, the crew used some Kapton tape to secure it back in position. I really love the idea of future shuttle commanders easing their multi-billion-dollar spacecraft up to the pinnacle of Russian spaceflight achievement, all while staring at an indicator that was just taped in place by an earlier crew. Continuing in the overall theme of the Shuttle Mir missions, a major goal of this flight was to mitigate risk. When designing their part of the International Space Station, NASA was going to have to make a vast number of technical decisions about things that they had little to no experience actually doing. So Mir presented an incredible opportunity to gather information and try different solutions in a lower stakes situation. If a particular solution didn't work here, then there was still time to learn from that mistake and redesign something new on the ground. Also, the more they knew about what they were getting into, the better they could design stuff in the first place. So, with that in mind, a lot of information about the Mir environment was being collected. On previous missions, samples of material and micrometeoroid collectors had been placed outside the station, so NASA could learn more about what life was like in this particular orbit. Joining that was a radio apparatus set up on the shuttle flight deck, which measured wide swaths of the spectrum, looking for potential radio interference. Since the ISS would be flying over more populated areas than Skylab, there were new opportunities for signals from the ground to become a problem. For the type of problem that comes from above, not below, radiation sensors were placed at 6 locations around Mir to get a good idea of what sort of radiation doses future ISS crews could expect, and how they might reduce that exposure. And samples of the microbial life both around the station and in the water supply were collected to get an idea of what might become a health hazard down the line. But, of course, the primary focus was on the transfer of various items and crew members. First of all, once John Blaha had installed his seat liner in the Soyuz and performed his entry suit check, he officially became a member of the Mir crew, and Shannon Lucid was free to join the shuttle crew. Lucid began to sleep and eat on Atlantis, though found that she preferred the bathroom on Mir. She asked Station Commander Valery Korzun if it would be alright if she continued to use Mir's facilities while Atlantis was docked, and he laughed and said that she would always be welcome in the Mir bathroom. But there were also literally tons of stuff that had to get moved through the hatch to the other side. Lucid had packed 21 bags full of scientific equipment, experiment results, and her personal belongings, and it all needed to return to Earth. On the shuttle, there were multiple experiments that had to get to Mir, along with food, clothes, and bags of water. We'll learn more about the experiments when we hear about John Blaha's stint on Mir, but for now, we're just moving them. All told, almost 2,000 kilograms of stuff went over to Mir, including 900 kilograms of water, and almost 1,000 kilograms of stuff came back to Atlantis. No word on if those mass totals included Blaha and Lucid. To help keep track of everything, the crew relied on a color coding system and a bar coding system. For color coding, the various bags were colored pink for stuff going from Atlantis to Mir, blue for stuff going from Mir to Atlantis, and white for stuff that was arriving on and staying on Atlantis. On top of that, Tom Akers served as a sort of load master, keeping track of everything floating in both directions. Helping Akers out was a system that allowed him to scan barcodes on each bag, updating their status in an electronic system. While this flight would transfer more gear than any previous flight, it was only going to get more complicated from here, so it was important to streamline everything as much as possible. Notably, this was the first time that experiments that required continuous power were transferred from the shuttle to Mir. Though, I gotta say, I was a little less impressed with this when I realized that they basically just unplugged the experiment and hustled it across to Mir really quick to plug it back in. Amid all of this work, the crews made sure to take some breaks to gather around together as a group. The shuttle crew reciprocated the Mir crew's hospitality and hosted them on Atlantis with a meal of Cajun barbecue, strawberry shortcake, and iced tea. The Mir crew were apparently pretty enthusiastic about the barbecue sauce, so the extra jugs were gifted to them to enjoy later. While a bunch of science was heading across the docking module to Mir for Blaha to operate over the coming months, Atlantis also had its own share of science experiments on board. This was possible because STS-79 was the first flight of the double-module Spacehab. Of course, we're now well familiar with Spacehab, the commercial variant of Spacelab. By providing extra pressurized volume in the payload bay, Spacehab greatly expanded the room available to the crew. We've flown a few times with a single spacehab module, but now we're flying with two, making a double long space at the end of the tunnel. The aft module was mostly used as cargo space for the various items coming and going from Mir, but the forward module was full of experiments that were just for this flight. Starting off, and you knew this was coming, there was the commercial protein crystal growth experiment. For those of you keeping track at home, this is the 31st time that commercial protein crystal growth experiments have flown on the shuttle, so no, you're not imagining it. This time, among the proteins being studied was one that causes asthma, and one that's important to the complement system, which is part of the immune system. The crew would also be operating an experiment studying the mechanics of granular materials. The press kit describes this as looking at the behavior of cohesionless granular materials in dry and saturated states at very low confining pressures. I'm pretty sure that when you translate that back into English, it means that they were studying sand, both wet and dry, that wasn't tightly packed into place. Once again, the idea here was that by removing gravity, it would be possible to better understand the surprisingly complex dynamics underlying the behavior of sand and other granular materials. Insights from this experiment could help engineers on the ground build more robust structures. We've also got the Extreme Temperature Translation Furnace. This, as you may have surmised, was a furnace that was designed to support extreme temperatures, up to 1600 degrees Celsius. The goal was to investigate how flaws form when casting or sintering metals. And as usual, this sort of knowledge was expected to allow metallurgists on the ground to make stronger and lighter materials. Unfortunately, the Extreme Temperature Translation Furnace turned out to be more of an extreme disappointment. The crew were to load in 4 different samples over the course of the mission. The first one wouldn't even fit due to it being structurally out of spec, but the crew were able to fix it and it was successfully processed. But when it came time to try samples 2 and 3, the circuit breaker kept popping, resulting in a maximum temperature of only 979 degrees, a paltry 61% of the goal. It was bad enough that they didn't even bother with sample 4. The experiment had required some last-minute changes after failing some checks, and thus time ran out for a proper pre-flight checkout, which I guess explains the trouble. Oh well, I guess that's what circuit breakers are for. And compounding the misfortune, the ETTF wasn't the only problematic experiment. As we've seen numerous times throughout the shuttle program, lots of experiments are extremely sensitive to vibrations. Even the small vibrations caused by the crew moving around up in the crew cabin can disturb experiments way in the back of the payload bay. And on top of that, there were also low-frequency vibrations that came from machinery and the dynamics of the vehicle. So, in an attempt to resolve this for the ISS, we have the Active Rack Isolation System, or ARIS. ARIS was an apparatus attempting to demonstrate the ability to isolate an experiment rack from the vibrations of the spacecraft it's flying in. ARIS used push rods, sensors, and active controls to damp out the vibrations it detected. Most of these were just the typical vibrations from day-to-day life on the shuttle, but it was also purposefully stress-tested with some thruster firings. ARIS seems like a pretty good idea to me, but it had some issues. The phrase divergent oscillation was used to describe the issues encountered. That's engineering speak for something broke and the whole thing started banging around and woke up the crew. This happened on flight days 2 and 5, so a new procedure was uploaded on flight day 7, only to reoccur once again that night. Nothing teaches lessons quicker than failure. After a frantic few days of activity, it was time for Atlantis to head home. After double-checking that everybody was on the correct side of the hatch, it was once again closed up tight as both crews prepared to separate. Both spacecraft momentarily disabled their attitude control systems, entering a free drift and ensuring that no surprise thruster firings would disrupt the departure. The hooks unlatched, the springs in the docking system smoothly pushed Atlantis, and after coasting for a couple of feet, Commander Reedy blipped the thrusters in a low Z configuration, gently backing away from Mir. For the next 2 hours, Atlantis slowly circled around Mir at a range of about 180 meters, while the crew took photos and shot video of the station, now in its final configuration thanks to the addition of Peroda. When the time came to once more fire the thrusters and finally leave the station behind, Pilot Wilcott noticed that Shannon Lucid had drifted to the aft windows to take one last look at her orbital home. Reentry and landing went nice and smoothly, but there was one minor hiccup that's worth digging into. As part of this mission, the pilot crew were going to perform a DTO, a Detailed Test Objective. This is the 79th flight of the shuttle, but engineers were constantly probing its limits and learning more and more about this magnificent vehicle. As part of this test, the pilot crew would execute a specific input with their flight controls, and the response of the vehicle would be compared to what was expected based on the simulation. For the test to be valid, some RCS firings needed to be inhibited, but when it came time to actually do it, the thrusters did in fact fire, executing a small yaw. This wasn't actually a safety issue, but it messed up part of the DTO, even if some of the test was able to be salvaged. So, what the heck? Why did the thrusters fire? They weren't supposed to, and they didn't fire when tested in the Shuttle Avionics Integration Laboratory, the high-fidelity testing facility on the ground. Well, it turns out that once again, the space program has gifted us a valuable lesson in the importance of configuration management. Normally, the RCS thrusters would fire when the shuttle drifted a little too far past a nominal state. You don't actually want these to fire right away, because otherwise the whole thing will just oscillate back and forth, constantly attempting to correct the quote-unquote error it was seeing. Instead, you set up a deadband where nothing will happen. Once you drift to the edge of the deadband, the thruster will fire and it'll drift back. It's sort of like how if you're driving down the highway, you don't frantically input steering wheel changes to stay right in the precise center of the lane. You sort of gently drift over near the limits of the lane and then make a gentle correction back. For this test, the limits of those deadbands were updated. Except, oops, not all of them. The configuration update was missing some of the deadband changes, so the computer instead went with the hard-coded defaults, resulting in the thruster firings. This should have just been an irksome discovery during testing, and should not have made it all the way to an actual flight. After all, that's why there's such extensive testing on the ground in the first place. But this brings us to another lesson. Test like you fly. The test was only performed during a higher pressure portion of the reentry, forgetting or missing that the computer switches between a low pressure and high pressure control scheme. In testing, they only tried the high pressure conditions, while the actual test was performed in the last bit of the low pressure period before continuing on to the high pressure. Which also explains why the thrusters stopped firing once they crossed from one mode to another. If you don't test under realistic conditions, you're not going to get realistic results. Okay, that's a pretty esoteric and dry way to wrap up an exciting space shuttle mission, but I just love those little details. One partially successful DTO later, Atlantis touched down at the Kennedy Space Center and rolled to a stop, closing out a mission lasting 10 days, 3 hours, 18 minutes, and 24 seconds. As the crew left the shuttle and walked over to a transport vehicle, they noticed that one among them had suddenly stopped. At first they were concerned that the crew member was feeling dizzy or faint after returning to 1G, but no, everything was fine. It was just that after 188 days, 4 hours, and 16 seconds, Shannon Lucid was enjoying the simple pleasure of feeling sunshine and a gentle breeze on her face. She was home. Next time, we'll rewind the clock a few days and hop on over to the other side of the hatch as we join John Blaha for his 4-month stay on Mir, where among other things, he'll encounter a new problem for the space program. Turns out, low Earth orbit is pretty far away from the nearest ballot box. Ad Astra, catch you on the next pass.